Okay, so today we're going to talk about section 1.5. Section 1.5 is transformations of functions. So we're going to talk about several different kinds of transformations. So to get us started off, we're going to talk about shifts. So we're going to jump right into an example here. To regulate temperature in a green building, airflow vents near the roof open and close throughout the day to allow warm air to escape. The graph below, the graph here on the left specifically, or ignore the graph on the right for now. The graph on the left shows the open vents V in square feet throughout the day, T hours after midnight. During the summer, the facility staff decides to try to better regulate the temperature by increasing the amount of open vents by 20 square feet throughout the day. Sketch a graph of this new function. I actually drew this new function a bit poorly here. Let me... So, this is actually a good opportunity here. So let's first look at V of t here. We see that from midnight until 8 a.m. there are no vents open. And then the amount of vents increase to 250 vents open by 10 a.m. It stays that way until about 6 p.m. And then they decrease back to 0 vents by 8 p.m. So during the summer, they are going to increase the amount of open vents by 20 square feet throughout the day. So notice how our baseline was 0, right? Outside of the times when these vents were open, all of the vents were closed. Now we're starting with 20 square feet worth of vents open. So that's why I have these horizontal lines. I'm going to start and end with 20 square feet of vents open. Then this is going to increase. I think I can't use the straight line tool here because it snaps to a grid, but we'll see. It needs to increase to a bit more than 250, right? It needs to increase to what I think would be 270 without having a 270 marker here. All right, there we go, I got it to work. And then it remains constant until about 6 p.m. And then it decreases back down to 20 vents. Let me see if I can better, if I can fix this end of it here a little bit. There we go. So this new function that we're calling s of t, in this new function, for each of my input values, my output values have been increased by 20. So this new function s of t, we could say, is v of t plus 20. It takes all of the output values of v of t and it adds 20 to them. So this tells me that for any value of t, s of t can be found by evaluating the v function and then adding 20 to the result. This defines the function s as being a transformation of the function v, in this case a vertical shift up 20 units. Notice here that my input values remained exactly the same. Now maybe my graphs look slightly different, but it's just due to my drawing and not due to them actually being different. And it's also due to like these stray dots here. So let's talk about vertical shifts. Vertical shift. Given a function f of x, if we define a new function g of x, as g of x equals f of x plus k, where k is constant, or where k is a constant, I suppose I should say. So k is just a number. In this case, g of x is a vertical shift I'll make this stand out here. G of x is a vertical shift of the function f of x where all of the output values have been increased by k. Keep in mind that all the output values could be decreased by k as well, right? If k is negative. So we say if k is positive, the graph will shift up. If k is negative, the graph will shift down. So let's look at a function in terms of a table here. Let's look at this function f of x from this table. So we have a table of x values and f of x values. We have the table, let's see, for x values we have 2, 4, 6, and 8. For f of x I have 1, 3, 7, and 11. Let's create a table for g of x equals f of x minus 3. So remember, with these vertical shifts, my input remains the same. It's simply my outputs that change here. So my inputs are still 2, 4, 6, and 8. However, in this case, let's see, if I want g of 2, for instance, this is going to be f of 2 minus 3. So that means that g of 2 is going to be, let's see, f of 2 is 1 minus 3, which is negative 2. And I can repeat this process for all of these, right? G of 4 would be f of 4 minus 3. F of 4 from that first table is 3. This is 3 minus 3, which is 0. And so I just subtract 3 from all of these output values to get the output values of this g of x. Again, notice that my input values here remain exactly the same. Let's see. All right. So let's also look at horizontal shifts. So we're going to look at the same problem that we looked at previously with the air vents, but let's suppose that in the fall, the facility staff decides that the original venting program starts too late, and they want to move the entire venting program to start 2 hours earlier. Let's sketch a graph of the new function. On the left-hand side, I sketched, again, the old function, the original venting program. And on the right-hand side here, I've sketched what it would look like if we moved the venting program to start 2 hours earlier. So instead of starting at 8 a.m., this starts at 6 a.m. And then instead of ending at 8 p.m., it ends at 6 p.m. So this means that, so I called this new function f of t. So if I compare the values between these, notice that, say, v of 8 is f of 6 here. Notice that v of 10 is the same as f of 8. So in both cases here, since f of t starts 2 hours earlier, the same outputs are reached when f of t is equal to v of t plus 2. Because I'm reaching these 2 hours earlier. So similarly, if I look at v of 12, for instance, v of 12, let's see, this is the same as what? F of 10, right? V of 12 and f of 10 would be the same thing. Or v of 20 is the same thing as f of 18. So, horizontal changes here, or inside changes, affect the domain of this function instead of the range. And these often seem counterintuitive, right? We might think that because this shifted to the left 2 units, that I should be subtracting here, right? But in fact, because this shifted to the left 2 units, that means that really these same values are occurring 2 hours earlier, right? So it's the same as if I had added 2 to the inputs of v of t. I hope that makes sense. So these often seem counterintuitive. Often these look like the opposite of what you kind of want them to look like. So let's look at horizontal shifts. Our definition here is going to be very similar to the definition that we had for vertical shifts. In this case, given a function f of x, if we define a new function g of x, as g of x equals f of x plus k, where k is a constant, then g of x is a horizontal shift of the function f of x if k is positive, the graph will shift left. Because I'm reaching these same inputs k units earlier. If k is negative, the graph will shift right. This is because I'm reaching these same input values k units later in this case. So let's look at the same function table that we looked at previously. We looked at the function, let's see. We had this table of x and f of x values, where for x values we have 2, 4, 6, and 8. My outputs were 1, 3, 7, 11. And this was the table for f of x. Let's find a table for g of x, which we'll define as being f of x minus 3. Well, let's see. For my x values here, we'll figure out what that's going to be. I know that my g of x values, my outputs, are going to be the same as in my original function. My outputs are going to remain unchanged here whenever I'm talking about these horizontal shifts. Let's see, 11. So let's see, if I'm saying that g of x is f of x minus 3, right, then I need for instance, g of 5, this would be f of 5 minus 3. So g of 5 would be the same thing as f of 2. So if I want to have the same output value as f of 2, then I have to find g of 5. A way of figuring this out is if I turn this into an algebra problem, right? If I want to have the same output value as f of 2, for instance, I need to take x minus 3 and set this equal to 2. And I solve for x and I get 5. What do I plug into g of x to get the same thing as if I found f of 4? I do the same thing here. I do x minus 3 equals 4. X equals 7. Okay, so you see that I'm adding 3 to these input values because inside these parentheses I'm subtracting 3 from them, right? So I'm going to reach the same output values later on in this function. Let's see, let's look at some graphs real quick. Let me go to Desmos. Oh, I didn't mean to do that. Although I suppose that's okay, but let me go to Desmos real quick. So let's look at this graph. Oh, I didn't mean to Well, I gave it away here, but that's okay. We can still look at this and figure out what's going on. So this is a transformation of the graph of f of x equals x squared of that toolkit function, the quadratic function. Notice here that this is, so normally my quadratic function has its vertex at 0, 0 at the origin. However, in this case, it has a vertex at the point 2, 0. So, as a result, this has been shifted to the right 2 units. So even if I hadn't seen this equation, I could tell that this is going to be shifted to the right 2 units. So I should have x minus 2 quantity squared inside of these parentheses here. Instead of having just x being squared, I replaced the x with x minus 2 in order to shift this graph to the right 2 units. And let's look at a few more graphs real quick. Let's look at the graph of the absolute value function. So this is the graph of the absolute value function. You see this is absolute value of x. Now, let's find f of x plus 1 minus 3. I'll type this down. I'll type what we're trying to find down here. This isn't going to be a graph, but I'll type this for us. I want to find f of x plus 1 minus 3. If this is f of x equals, oh, I didn't know you could do that in Desmos. Okay, I didn't know you could define a function like that. I just learned something. So I want to find f of x plus 1 minus 3. So I could break this down. Like if I were sketching this by hand, I could break this down by each of these transformations. I could do these individually, right? Just so I could maybe see how each of these is affecting the graph of this function. So I could do absolute value of x plus 1 first. And notice that, so absolute value of x plus 1, this is the green graph. So from the red graph on the right to the green graph on the left, I shifted left 1 unit. That's how this, that's how replacing this x with an x plus 1 affected the graph. And then if I subtract 3 on the outside, here, let me make another graph here, x plus 1 minus 3. To go from the green graph to the purple graph, all I did was shift down 3 units. Yeah, apparently you can define a function in Desmos as saying, if you say something like f of x equals x, you can then type in f of x plus 1 minus 3 if you want to define that. That's interesting. I didn't know that. I genuinely didn't know that before. Okay. Wow. That's cool. Let's see. Let's look at this one. let's try to figure out what this is the graph of. So this, I'll tell you that this is a transformation of the square root function. This is a transformation of the square root function. I'll zoom in so we can see the numbers better. So the square root function normally starts at 0, 0. But in this case, it's starting at 1, 2. So as a result, this has been shifted to the right 1 and up 2. This means that I need to replace my x with an x minus 1. Since replacing x with x minus 1 means I shift to the right 1 unit. And then outside of the function, I need to add 2 units to shift all of my output values up 2 units. And we end up with square root of x minus 1 plus 2. Okay. Now let's look at reflections. Maybe I'll start there we go. Reflections. Let's reflect the graph. Of s of t equals square root of t both vertically and horizontally. Let me go ahead and graph this for us. Let's see, I guess maybe it's best for me to have 3 different Desmos open here. So we'll start with the regular square root function, the base square root function. This is what square root of x looks like. If I just graph square root of x, this is an increasing function. It's concave down. It's going towards the right. The domain here would be 0 to positive infinity. I would include 0 with a bracket because, as you can see, I have a point defined there. Now, if I wanted to reflect this graph vertically, it would look like this. Let me close this one. If I wanted to reflect this graph vertically, it would look like this. Notice that here, all of my output values are opposite in sign to the output values of my original graph. This is reflected across my horizontal axis here, right? So since each of my output values is opposite of my original output values, this is just negative square root of x. So you see, I'll once again graph square root of x. In the blue, this gets reflected across this x-axis to become negative square root of x. So notice that this is an outside or a vertical change and this only affects my output values. My input values are completely the same, right? So because this is an outside change, this is a change in my outputs, that's why the negative sign goes on the outside of the square root here. And now I want to reflect this horizontally. And this is my graph. Oh, I gave it away, but you probably already figured it out, right? If I reflect horizontally, each of my input values are reflected across my vertical axis. Since each of my input values are the opposite of my original input values, because we can see here if I graph square root of x, each of my input values in this red graph are opposite the input values of my blue graph here. They're simply opposite in sign. That's why this is the square root of negative x. This is a change in my inputs, so the negative sign goes on the inside here. Notice that this does not mean that I have a negative number under the square root, because in this red graph, for instance, right here, right, the square root of minus -5, or the square root of -5, is the same thing as the square root of 5. So my output values remain unchanged because I have a double negative under the square root for all of these numbers. My output values remain unchanged. It's simply my input values that have been changed, and that's why this negative sign is under the radical. My domain here for this red graph is -infinity until 0. I'd have a bracket with that 0. So let's get some definitions of reflections here. Similar in definition to the other things. Given a function f of x, if we define a new function g of x as g of x equals negative f of x, then g of x is a vertical reflection of the function f of x sometimes called a reflection about the x-axis. Similarly, if we define a new function g of x as g of x equals f of negative x, then g of x is a horizontal reflection of the function f of x sometimes called a reflection about the y-axis. So we're going to take that same table from earlier and we're going to reflect it. So the table that we had earlier, once again, was this one. And I have this f of x here. I had 1, 3, 7, and 11 were my f of x values. Let's create tables for g of x equals negative f of x and h of x equals f of negative x. Let's see how this affects this table. Let's see, for g of x, my input values are all going to be the same. These are going to be 2, 4, 6, and 8. But now my output values are going to be opposite in sign from the output values of f of x. So I'm going to have negative 1, negative 3, negative 7, and negative 11. For h of x, let's see. I'm going to have all of the same output values. I'm going to have, this is h of x. I'm going to have 1, 3, 7, 11. These are positive this time. But my input values are going to be opposite in sign of the input values that I had for f of x. So these are going to be negative 2, negative 4, negative 6, and negative 8. Now let's talk about this idea of, let me think. Maybe I should, I'm gonna stop this one here. I'm just going to split this into another lecture so I can do the odd even and the stretch and compression stuff in the next lecture right after this one.